Hello, everybody. Today, the discussion sheet has a bunch of problems on probability and independence. So let's dig in. So we're starting off with basically this big graph right here. It's a Bayes network, and it's going to help us calculate some fun conditional probabilities. So let's look at it. So a patient can have a symptom S. So let's highlight S is this thing that can be caused by two different independent diseases, A and B. So let's color those in too. A can be is here and here and here, and B it can be green, which is this node, and here and here. And there's the variation of a gene G, which plays a big role in the manifestation of disease A. So G can be blue. It's this one. I've got a table for it here. All right. So modeling some conditional probability tables for the situation are shown below. For each part, you may leave your answer as an arithmetic expression. So what we're saying is that probability of just getting G at all is 0.1 that you have the gene and 0.9 that you don't. All right. What about the probability that you have A, given that you have G? Well, that's given by this table here for each value of A and G. Probability that you get B at all, which is just independent of whether you have A or whether you have G, is 0.4 that you do, 0.6 that you don't. And then finally, we get this big table here, which is probability that you get the symptom, given that, you know, whether or not you have A and whether or not you have B. So first, we're going to compute this entry from the joint distribution. All right. So what's the probability of G given A, B, and S? Well, we can sort of expand this out by going from top to bottom in the graph. So it's the probability that you have plus G times the probability that you have that you're positive for disease A, given that you're positive for gene G, times probability that you're positive with disease B as well, given that you're positive of disease A and given that you're positive with gene G, times the probability that you're positive of the state of the symptom. Sorry, I'm used to S being state, but here it's symptom. So probability that you have the symptom, given that you do have the gene and that you do have A and that you do have B. So what this this graph is telling us is basically that that some of these terms we can simplify because there's independence. So because A only has an array from G, okay, probability of G, we can't simplify that further. Probability of A given G, well, A has an array coming down to it from G, so we can't simplify that. But B given A and G, there are no arrows going from G to B or A to B, right? These don't exist. They aren't there. So that is actually just the unconditional probability of B is what that is equal to. Then finally, probability of plus S given G, A, and B. Well, we have like this array to S from A and this array to S from B, but there's no array from G, right? This red array doesn't actually exist in the diagram. So what that means is we can just ignore the plus G. We'll move that around a little bit, put it up on the same line as the rest. So this is all we have to calculate. So let's calculate it. So probability of plus G, if I look that up in the table, that's 0.1, right? Now plus A given plus G, so in this probability of A given G, there's plus and plus. So here the answer is 1.0. So multiplied by 1.0. Now probability of plus B, here we can see that that's 0.4. And probability of S given plus A plus B, so that's this all pluses row in probability of S given AB, so that's by 1.0. All right, so that's 0.1 times 0.4, just ignoring the factors of 1, which is 0.04. So hopefully this gives you a sense of like just what is going on with these Bayes diagrams and with these Bayes networks, I should say, and like how you actually get any probabilities out of them. All right, let's remove some of my scribblings. Yeah, just this stuff that makes it hard to read. Oh, but, okay, we've covered probability of G. All right, next question. What is the probability that the patient has disease A? So basically, our job is going to be to write it in a way that we're using like, numbers here, right? Because we have those numbers, so we just want to get probability of A in terms of those numbers. So what we can do is we can remember the law of, I guess this is marginalization or something, but essentially it's the rule that probability of A is, or probability of plus A is probability that you're positive for disease A, given that you're positive for disease G. Actually, let me simplify that. It's probability that you're positive for A and you're positive for G, plus the probability that you're positive for A and you're negative for disease G. And that's true because, either if you have A, you can either have it by having G, or you can have it by like not having the gene. But, those are the two ways kind of you can have disease A. Now, because we want to have things in terms of probability of G and probability of A given G, we can expand this out. So probability of A and G, probability of positive A and positive G, well, that's equal to the conditional probability of positive A given that you're positive G times probability that you are positive for G at all. And similarly, probability that you're positive for A and negative for G, that's equal to the probability that you're positive A given that you're negative for G times probability that you're negative for G. And that's actually just because of the definition of conditional probabilities, like probability of X given Y is probability of X and Y divided by probability of Y. So, you can just rearrange this, put this over here, and I guess remove this line, and that's basically what we used. All right. No, actually, I won't erase this. All right. So now we have, so the point of all that is that we now have like probability of A given G and probability of G and probability of A given G and a probability of G. And these are numbers that we just look up in the table, in the tables provided. So what's that? Probability of being positive for A given that you're positive for G. So that's positive in this A given G diagram. So that's 1.0. What's the probability that you're positive for G? That's 0.1. Plus probability that you're positive A given that you're negative for G. So that's a negative G positive A term in this table, and that's 0.1. And what's the probability that you're negative for G? That's 0.9. All right. So what's that? That's 0.1 plus 0.09, which is 0.19. All right. Next question, we've got a conditional probability. What is the probability that a patient has disease A given that they have disease B? All right. Well, here we have to remember that A is independent of B. How do you know that A is independent of B? Well, it says so, right? They're independent diseases. You can also, well, we'll get later into this thing called d-separation, which is once you have d-separation, you're just going to look at this graph and you're going to be like, I can tell they're independent, but we don't have that yet. So we'll get to it later. But for now, it just says in the question, they're independent. So if they're independent, then probability of positive A given that you have positive B, is just probability that you're positive for A. And what's that equal to? Well, we calculated it above, right? It was 0.19. So the answer is 0.19. And I'll move this independence assertion so that you can see everything a bit more clearly. All right. Next question, we're gonna have a less colorful graph. I'm sorry. And correspondingly, we're gonna have a little bit trickier problems. So probability that you have A, given that you have the symptom S and you have the disease B. So we've got positive A, positive S, and positive B. But it's not exactly like this is like this expression here is A given S and B, and this expression here is S given A and B. So again, we're going to want to massage this to get it to something that we actually can calculate more easily. So how are we going to do that? Well, first, we're going to use the definition of conditional independence. So this is probability that you're positive for A and positive for B and positive for S divided by the probability that you're positive for B and you're positive for S, right? So on the top, we have A, positive B, positive S. Like we can kind of figure out how we would calculate that. On the bottom, we only have just B and S, right? Which is not really natural, but we can reintroduce A because like A, B, and S are kind of tied. Oops, they're kind of tied together here. So it's going to be useful to have the trio of them. The way we're going to do that is, again, we're going to use this law of, I guess, total probability, which is probability that you're positive for B and positive for S is equal to the probability that you're positive for A, positive for B, positive for S, plus the probability that you're negative for A, positive for B, positive for S. Right? Because either you're positive for A or you're negative for A. All right, so we'll move this expression over a bit, and then we'll think about it a little bit more. All right, so how would you calculate the probability, positive for A, positive B, positive S? Well, the thing you can do is this is just equal to probability that you're positive for A, which remember, we calculated here, right? It was 0.19. In fact, I'll just write that down here. Probability that you're positive for A equals 0.19. All right, so it's probability that you're positive for A times probability that you're positive for B, given that you're positive for A, times probability that you're positive for S, given that you're positive for A and positive for B. All right, so we have probability that you're positive for A, probability that you're positive for B, given that you're positive for A. Well, they're independent. So that's just probability that you're positive for B at all, right? Now, probability that you're positive for S, given that you're positive for A, positive for B, well, that's just in the table, right? This table right here. First row. So this is pretty good. We can replace the expression up here. So that was probably that you're positive for A, B, and S. So we can actually copy paste that to replace it, the term on the left on the bottom. So copy, we'll erase this, and can Daniel copy and paste? Paste. All right. Here we are. And then probability negative A, positive B, positive S. It's basically the same thing, but use a negative sign. Because like this law didn't depend on whether we were talking about positive A or negative A. So we're going to replace it by this, and then we're going to replace every plus A with minus A. So it's plus turns into a minus, and this plus here turns into a minus. Okay, now we've got to turn those into numbers. What's the probability that you're positive for A? 0.19. 0.19. Probability that you're positive for B, that's 0.4. 0.4. Actually, I'll do this. I'll do A everywhere. So, okay, on the bottom, here's probability that you're positive for A. Replace that with 0.19. And probability that you're negative for A. Well, it's 1 minus probability that you're positive for A, because either you're positive or you're negative. So that's 1 minus 0.19. So 0.19 is 0.01 under 2. So this is just going to be a little bit bigger than 0.8. It's going to be 0.81. Yeah. All right. So probability that you're negative for A, 0.81. Now, probability that you're positive for B, again, it's here, 0.4. And the second sub-expression on the bottom is also 0.4. Now, the probability that you're positive for S, given that you're positive for A and you're positive for B, that is 1. It's first row in the table above, right? So times 1.0. And here, first term on the bottom is times 1.0, because positive S, given that you're positive for A, positive for B. Then probability that you're positive for S, given that you're negative for A, positive for B. So that's, we want minus plus plus, right? Minus plus plus. So negative A, positive B, positive S. So it's this term. So that is 0.8. All right, let's multiply this out. What's 0.19 times 0.4? The thing I have in front of me tells me that it's 0.076. And on the bottom, 0.076 again. Plus 0.81 times 0.4 times 0.8. I'm told that's 0.2592. You could use a calculator, but I just have the results in front of me, so why not? And this fraction is approximately 0.2267. So if you have symptom S and you have disease B, you're not that likely to have A. So there you go. But you're still a little bit more likely to have A than, you know, if you just an average person. All right, next question. What is the probability that a patient has a disease-carrying gene variation G, given that they have disease A? So probability that you're positive for G, given that you're positive for A. So here we want to use like these numbers, right? And in particular, we have A given G, but we don't have G given A. So we're going to use everyone's favorite rule, Bayes rule. All right, so this is equal to probability that you're positive for A and that you're positive for G, divided by probability that you're positive for A, right? Well, that's equal to probability that you're positive for G times probability that you're positive for A, given that you're positive for G. And this bottom is probability that you're positive for A and positive for G, not times, plus rather. Plus probability that you're positive for A and negative for G. Okay, but again, we can just do the simple expansion where probability that you're positive for A and positive for G is probability that you're positive for G, probability that you're positive for A, and given that you're positive for G, and then probability that you're negative for G times probability that you're positive for A, given that you're negative for G. And this is good because we've massaged it until we have these terms in like priors, you know, just overall probabilities, but you have G, and then which is like this table right here. Yellow is not the greatest color. Oh well. And probabilities of values of A given values of G, which is this table here, right? So we're ready to do this. So let's plug in some numbers. So probability that you're positive for G is 0.1. probability that you're positive for A given that you're positive for G. So that's the positive row right here, which is 1.0. Now, again, one nice trick is that this term here is the same as the thing on the top. So you can just copy. So 0.1 times 1.0 plus probability that you're negative for G, that's 0.9, plus probability that you're positive for A, negative for G, that's the negative G positive A right here, that's 0.1. So 0.1 divided by 0.1 plus, and you know what? Here, where we had this probability of A, we could have just, we already calculated this. Why did I calculate that out? That was silly of me. So remember, you can, your teachers are not perfect, but I'm going to get the right answer anyway. So I'm not that imperfect. So 0.1 plus 0.09, which is of course 0.1 divided by 0.19. So the quick and dirty thing is 0.19 is approximately 0.2. So this is about a half, but it's more accurately 0.5263. All right, so there you go. And the thing, basically the moral of the story here is that you weren't that likely to have gene mutation G, right? You actually only had a 0.1 chance of getting G. But because like you definitely had G, if you had G, you definitely had A. And if you didn't have G, you probably didn't have A. A is like a pretty decent test for whether you have G. And like this chance that G was wrong, the chance that like you would have A without having G was about the same as the chance that you would have G at all. So like, 1 out of 2 surprise, if you have A, then 1 out of 2 surprising things needs to happen. Either you have G, which was kind of surprising, or you didn't have G given that you had A, which was about equally surprising. So that's a way to kind of convince yourself that like, yeah, the probability here should be around half. If you ever want to do these calculations in your head, but like not actually exactly. All right, so let's move on. Now we're going to do independence. So this is the fun situation where you can cut some corners in calculations and you don't have to be wrong. So you have 2 random variables, C and N. C, you flip a bias coin that lands on heads with probability 0.8 and tails with probability 0.2. N is the number of heads that result from 2 independent coin flips of a fair coin. All right, so probability of C, well, it says that it lands heads with probability 0.8. So we can fill in this entry. How likely is it to land tails? 0.2, right? 1 minus 0.8. All right, now the number of heads that result from 2 independent coin flips of a fair coin. Well, with a fair coin, there are 2 ways of getting heads and tails, right? Like the first could be heads, the second could be tails, or the first could be tails, or the second could be heads. That's out of 4 possible options. So 2 out of 4 is a half. So there's a 1 in 2 chance that there's only 1 head. How do you get 0 heads? Well, they have to like both be tails. So that's one way of having it happen out of 4. So 0.25. And similarly for them to both be heads, there's only one way for that to happen out of 4 possible ways, things you could happen when you flip 2 coins. This is also 0.25. All right. Now, what's the probability of C and N? Well, the thing is, these are independent events, right? There's nothing, there's no like physical process connecting what happens when you flip a bias coin with what happens when you flip some fair coins. And there's no logical connection. Like there's no reason that one tells you the other. So C is independent of N. So probability of C and N is probability of C times probability of N. So, okay, we just calculate things. So H, probability of H is 0. Well, it's 0.8 times 0.25, which is 0.2. H in 1, 0.8 times 0.5, which is 0.4. H in 2, 0.8 times 0.25. We already did this, 0.2. All right, 0.2 times 0.25. That's 0.05. And tails 2 is the same as tails 0, right? Because these are the same. And tails 1, 0.2 times 0.5, that's 0.1. So, and we can add these up to check that this is really a probability distribution. Do they really sum to 1? So 2 plus 4 plus 2 plus 1 is 4, 5, 6, 7, 8, 9. Plus 0.05 plus 0.05 brings us all the way up to 1. So it's good. We succeeded today. All right. Next question, what is probability that n equals 1 given that c equals t? So probability that you land, that you have 2 independent coin flips of a fair coin, you got 1 head, given that your bias coin landed tails. Well, it doesn't matter that the bias coin landed tails because C is independent of n. It's still independent of n, even, okay. So what that also means is that probability of n equals 1 given c equals t is just the probability that n equals 1. Doesn't tell you anything. C doesn't tell you anything about n. So probability of n equals 1 given c equals t is probability of n equals 1, and that is 0.5. So you can see how that made life a lot easier, right? We didn't have to use Bayes' rule. We didn't have to, have this big fraction with a bunch of terms in it. It was just, life was nice. Things are nice when things are independent. All right. Now simplify each of the following into a single probability expression using the given independence assumption. So we're going to be able to simplify things given independence. So that just shows how great it is. So A is independent of B, simplify sum over A, probability of A given B, probability of C given A. All right. So probability of A given B, probability of C given A. Well, if A is independent, I'll just write that out so that I can manipulate it myself. Probability of C given A. And here, this little a is ranging over values of big A. And B and C are just arbitrary values of big B and big C. All right, so if A is independent of B, then probability of A given B is just probability of A. Because like B tells us nothing about whether A was true. All right, so now we're summing over A, probability of A times probability of C given A. Well, that's just product of A and C. It's the probability of A and C, right? It's the product rule. Probability of A and big C. Now, by the law of total probability, what's the sum of all the ways that A can happen? Probability of A and your given C? Well, it's just probability of C, right? What's the probability that, I eat toast for breakfast and that I eat olives for dinner, plus the probability that I eat, something else for breakfast, times the probability, and that I eat olives for dinner. It's just the probability that I eat olives for dinner. That was a weird example. I'm not going to eat olives for dinner today. I won't. All right, given that B is independent of C given A, simplify this thing, which let's write that bigger so that you can, probability of A, probability of B given A, probability of C given A, divided by probability of B given C, probability of C. And we know that B is independent of C given A. So we want to look for a thing that has A, B, and C in it. And if we look, the thing that we can notice is these terms here, right? Probability of B given A, probability of C given A. Remember that when two things were independent, you can write their joint probabilities as the product of their marginals. It's sort of the same thing with independent, with conditional independence. Probability of B given A times probability of C given A is equal to probability of B and C given A, given that because they're independent given A. So conditional independence, it's kind of like normal independence, but just everything is conditioned on the thing that the independence is conditioned on. So all right, we can simplify this fraction a bit, we'll throw this expression here. All right, now let's look at the top. Probability of A times probability of B and C given A. Well, that's probability of A and B and C, right? So we'll replace that by probability of A and B and C. Now at the bottom, probability of B given C times probability of C. Well, yeah, this is the, I don't know, the chain rule or whatever. That's probability of B and C. So, sorry, I don't really remember the names of these rules. They're just rules to me. They're just background in my life. All right, so probability of A and B and C divided by probability of B and C. Well, that's just exactly what conditional probability is. This is probability of A given B and C. And that's pretty simple. That's a single probability expression. All right. So given that A is independent of B, I'll erase this. You don't want to care. We don't care about that anymore. Given that A is independent of B, given C, simplify probability of C and A given B, probability of B divided by probability of C. Let's write that out bigger. So probability of C and A given B, probability of B divided by probability of C. All right. Well, the thing that is kind of obvious is that it's top C and A given B times probability of B. Again, that's just equal to probability of A and B and C, right? Probability of A and B and C divided by probability of C. All right. Now, again, we have this is just conditional probability. This is probability of A and B given C. All right. Can we simplify that further? Well, it depends on what do you mean by simple. Well, A is independent of B given C. So what this means is that we can write this out as probability of A given C times probability of B given C. Is that simpler than probability of A and B given C? I'll let you judge. It's more terms, but the terms are smaller. So there you go. All right. Now finally, we're marking all expressions that are equal to probability of R and S and T given no independence assumptions. All right. So the first one, probability of R given ST, probability of S given T, probability of T. Well, how would you get something like that? So probability of R and S and T. Well, it's probability of T times probability of R and S given T. And now we can sort of do the same trick to the right hand thing. So probability of R and S given T is probability of S given T times probability of R given S and T. But that's just exactly the thing that that's up there. So this one is equal. Very good. Okay. How else could we do it? We're going to try and write it to be like this one here. Okay. So we start off by getting, I don't know, maybe probability. Oh, that didn't work. Okay. Probability of S times probability of R given S times probability of T given R and S, right? And now what we notice is that, okay, this probability of S here, that's the term we had. This probability of T given R and S term here, that's the term we had. But there's a problem, right? Here we have probability of R, here we have probability of R given S. And probability of R does not have to be equal to probability of R given S. That's only true if R is independent of S. So this one, not equal. Brr. All right, sad. Next one, delete this, but return the equal sign. Okay. So here we're breaking out into probability of t times probability of s given t. And then we'd have to go to, for it to be equal to probability of r and s and t, I guess we'd have probability of r given s and t. And now we can see that there's exactly one term different, right? R given s here, R given s and t down here. But probability of r given s does not have to be equal to probability of r given s and t. That's only true if r is independent of t given s. So this is not equal, given no independence assumptions. So for next round. So here, probability of r given s and t, probability of s given r and t, and then probability of t given r and s. Yeah, this is a funny one. So how do you get that? So it would be like probability of s and t times probability of r given s and t. And now the question is, can you, big question mark equals, can that, or hang on. The question is it the case that probability of s and t is equal to probability of s given r and t times probability of t given r and s? Is it? Well, we know that probability of s and t, that's equal to probability of s times probability of t given s. So could it be the case that these are just definitionally like have to be equal? Well, no, because there's dependence on r, right? Like there's no particular reason that for every value of r this equality should hold, because it doesn't follow from any of the laws of probability that we have. In order to like really rigorously prove this, I would have to like give an example of a table of probability of like r and s and t for a bunch of values. But I don't know. I think if you just pick a random table, you're gonna succeed at showing that this isn't necessarily true. So that'll be extra homework for you. So this doesn't hold. This equality does not hold without further independence assumptions. Of course, if you did have independence assumptions, right? If s, t, and r were independent, then this equality would hold, because you could just condition on whatever, wouldn't matter. But for now, we're going to leave this by, and we're going to go to our next question: probability of r, probability of t, and s given r. Well, that's I mean, you could just multiply that out, right? That's just I guess the chain rule that always holds. So yeah, this is equal to probability of r and s and t given no further assumptions. Next one. So this is also just the chain rule, except we're sort of we're doing it with this variable r comma s that you might think of as two different variables, but you can just to make it easier, you can define x as the vector where the first element is r and the second element is s, and then this is basically the same thing as probability of t given x times probability of x. So this is equal given no further independence assumptions. So we can check that. Then none of the above. Well, we've already found some things that are equal, so it can't be none of the above. All right. Well, that's the end of the session. I hope this has given you a better sense of what's going on with independence, and also what's going on with these Bayesian networks. All right, I'll talk to you again next week. Goodbye.